So first, I want to thank Professor Kessler for a very kind invitation. It's a pleasure to be even virtually there in Turkey, in Ankara. So when it comes to my background, I can add, I did my master's degree in Poland. Originally, I am from Poland. And then more than 30 years ago, I moved to Canada, where I did my PhD in the area of mathematical statistics. And then I became interested in area of mathematical finance. So this was the time where many important questions were still open. Some of the questions were related to proper pricing and hedging. So gradually I learned how to approach the different problems and had a chance to make my own contributions. So the topic for today is one of the classical topics in modern finance. It is about hedging. So maybe, yeah, this is the outline. What it does, what we are going to do in the talk, we will talk about certain shortcomings of the standard delta hedging method that we uncovered in our study. The discussion will be focused mostly on Asian options, but the problem that we uncovered for delta hedging is valid for almost all path-dependent options. So when you read papers, textbooks, typically it is assumed that delta hedging for such options has similar properties to delta hedging for European options. As we will see, however, this is not the case. The standard delta in the context of Asian and path-dependent options artificially increases hedging error. And as we will show, to find the proper hedge ratio requires much more work than simply taking derivative of the price of the option with respect to the spot price of the underlying security. So to first formally detect the problem, in the talk, initially at the very beginning, I will go very quickly through basic concepts. I wasn't sure about the background of the seminar participants, but to uncover the problem, we will compare delta hedging with the mean square optimal hedging. And we will do this both in the context of European option and then path-dependent options to see the difference. Once we identify the problem, we will propose a solution. And as you will see, it's not as easy, as simple as the one we use for delta hedging, but it is working well. And at the very end, I will mention open problems. What I have done, I believe, should be of interest to academics and practitioners, but still much more work is needed to really, for this solution to be accepted. All the results that I present are in the context of the Black-Scholes model, and I will explain this in a moment, but they are actually valid for any diffusion type model, like the Heston stochastic volatility model. So I don't want to make impression that this is confined to a very particular model. It is actually valid across all different models. At the very end, time permitting, I will mention different way of hedging of path-dependent options, which complements the first part. I don't expect that I will have a lot of time, but what will be really important are the general remarks that I should be able to make at the very end. So the talk is based mostly on the first paper, which was published in Science Journal of Financial Mathematics, and all the mathematical details can be found there. I will not present a lot during the talk. I will focus mostly on intuition and basic facts. The last part of the talk is based on another paper also published already. So all the mathematical details can be found. So actually, maybe after the talk, I will send a slide to Professor Kessler on the information. So very briefly, what options are about. So we are going to talk about financial options, which are financial contracts whose value is contingent on the value of another underlying traded security. So for the purpose of this talk, we are assuming that the underlying security is traded. For example, this could be S&P 500 index. More generally, options are applied in situations where the underlying is not necessarily traded security. This could be in the context of insurance products or energy markets. But we are using very classical framework. And this actually is important because the problem that we identify with the traditional delta hedging appears even in very nice situation where all the assumptions are adopted as in Black-Scholes framework, the nice framework, and still we find some problems. So basic example of an option is a call option or a put option. These are so-called vanilla options. A call option gives the owner the right, but not the obligation to buy the underlying asset at predetermined price, which is called strike price, at predetermined time period, which is called maturity. So we are going to denote the price of the underlying security using letter capital S. So this is at the bottom. And then the payoff function of a call or a put option at maturity can be represented using mathematical symbols. So at the bottom on the left side, there is payoff function of a call option, which is piecewise linear function. Actually, it resembles hockey stick shape. Put option is also piecewise linear function. More generally, for European options, the payoff is determined by certain function of the terminal value of the security. So again, this is capital S at maturity, capital T. And there are many ways options are used, at least in the context of financial markets. For example, to hedge risk. If I now own a particular security and I expect that its price may decline, I can buy protective put. This will protect my position from a decline in the value if the underlying goes down. So this is one example of application. Another application is to reflect view on the direction of the market. Instead of buying the underlying index, I can buy a call option. Then other applications is to find arbitrage situations to change the nature of liability or to change the nature of investment. So the last two are in the context of swap options. So there are some examples. They are widely used. The problem that we want to look at is the one of hedging. So owner of an option, let's say call option at maturity, is entitled to a certain amount or will get nothing. There is no risk for the owner. For the writer of the option, however, there is risk. And the risk is uncertain, potentially unbounded. So typically, writers or issuers of options, they hedge their position. And there are different ways of doing this. Could be through creating a static hedge. And time permitting at the very end, I will say a little bit more about this. However, static hedges usually do not remove completely the risk. However, there is another way of hedging, actually replicating the value of the option. This is through so-called dynamic replication. So we create portfolio that consists of position in the underlying security, again, let's say the index, and bank account or bond. By continuously rebalancing this portfolio, we know that it is possible to hedge perfectly any contingent claim. And then the number of shares in this portfolio can be determined using different methods. The standard approach is the delta hedging, but there are other approaches like mean square hedging or mean square optimal hedging. This is what we are going to talk in a moment. Other approaches include quantile hedging or stop loss start gain hedging. So in this talk, we will focus on options that depend on the path of the underlying. So formally, option like this can be represented as a functional defined on the space of trajectories of the price process. And basic example, and this is the one that we will focus on during the talk, is so-called Asian call with a fixed strike. So if you look at the payoff function, instead of the terminal value of the underlying at maturity, which would be price of the index, we replace this with a functional defined on the space of trajectories. In this case, the functional is integral of the price of the underlying security, and we divide by the length, so we take the average. Other path-dependent options include American options, Bermudan options, barrier options, look-back options, ratchet options. There is a large number of options that depend on the path. Many of these, like barrier options or look-back options, even Asian options, are considered exotic contracts in a sense that they are traded over the counter. They are not exchange traded. However, American options are widely traded. These are actually the most traded options, and they are still path dependent. So they have this element of optimal decision on the part of the owner of the contract. But by now, we have good understanding how to go to identify the optimal decision. And quite often is in the form of a barrier. As soon as price drops, for example, for American put option, as soon as the price of the underlying reaches the barrier, the option should be exercised. So this means, in a sense, it is a barrier option and it is path dependent. So whatever problems with delta we find, actually they apply also to American options. So what delta hedging is about? It is actually a delta we can look in two different ways. Delta is one of the so-called Greeks which measure sensitivity of an option when one of the input values is changed. In the case of delta, this is first derivative of the price of the option with respect to the value of the underlying security. So this is one application of delta. It is a measure of sensitivity of option price, more generally our position, so this could be in the context of a portfolio, with respect to the change in the value or market value of the underlying security. Now, other important application, the one that I already alluded to, is for hedging. And it can be shown, you will see actually the outline of the proof I will show in a moment. In the context of so-called complete market models, it can be shown that the number of shares in the portfolio obtained in this way can be used to dynamically replicate the value of any option. So how can we justify this? So this is an easy explanation. Some authors refer to this explanation as business school type explanation of the form of the delta. So suppose that I sold a call option. So this is why in the portfolio we have minus sign. And I want to add position in the underlying plus possibly cash position so that overall the portfolio is insensitive to the change in the value of the underlying security. How can we quantify, how can we measure the change? Simply, we can find derivative of the value of the portfolio with respect to the price of the underlying and equate to zero. So if I calculate derivative and equate to zero, we find that the position in the security should be equal to the derivative of the price of the option with respect to S. This is quite intuitive explanation. However, it's not correct because formally, we are creating replicating portfolio where the hedge ratio A constantly changes with S. So formally, A also depends on S, and I cannot pretend that it is constant. But in this derivation, we pretend that it is constant, and this is why it is not proper mathematical justification for delta hedge. The proper justification uses stochastic calculus, and I'm going to go very quickly through the steps because also by doing this, I'm going to introduce important components for our discussion later. So to demonstrate formally that it is possible to create a replicating or hedging portfolio, first we postulate certain dynamic for this price of the underlying security. And this is done using diffusion type process that solves stochastic differential equation. So we do this under the empirical measure P, means we are postulating model that in principle we should be able to estimate if I observe prices of the index in the market. So this model is in the form of stochastic differential equation. It is a linear stochastic differential equation because both the drift term and diffusion term are linear function of the underlying security. There are two parameters. The first parameter nu is the instantaneous expected rate of return. And the second parameter sigma is the volatility. So we have to specify these two parameters. And the driving noise here is Brownian motion. So for those who are not familiar with this concept, you can think about this as a limit of properly scaled random walk when the values of the walk are interpolated using linear functions. So in the limit, we will obtain function that is defined for any real argument and is often referred to as continuous random walk. So this is standard Brownian motion. This particular stochastic differential equation can be solved explicitly, and the solution actually is given here. And this is one of the reasons this model is so popular as a mathematical framework within which we can derive many useful results, because we can do a lot of mathematics. In particular here, we can show that the distribution, the price of the underlying follows under this model is log normal, which follows from this representation of the solution of this differential equation. Now, second component in our model will be bond. However, under the assumption typically adopted for this simple derivation that interest rate is a constant instead of bond, rather we deal or use bank account, which grows at certain rate R, which corresponds to the interest rate. So we have two components, and we want to create portfolio where we trade the underlying security and also deposit or borrow money in the bank account that has the property that at any time is equal to the price of the option. So we have to find the trading strategy A and B such that the corresponding portfolio at any time is equal to the price of the option. We still don't know the price, but what we are doing here, we are postulating that the price of the option is a function of the current spot price and time, which actually corresponds to the length of the remaining time period until maturity, because maturity capital T is fixed. We also insist that this portfolio is self-financing. This means I can rebalance this portfolio only using the wealth generated by this portfolio at any time. So this translates to particular dynamic of the portfolio as represented at the bottom. The portfolio must have this particular representation. Formally, if I used Ito's lemma, we would have more terms. But if I insist on the portfolio being self-financing, this is the right representation. And now, what do we do with this framework? By the assumption that the price of the option is a function of the current spot price of the underlying, I can also find the stochastic representation for the price of the option. So this is stochastic integral representation for the portfolio. I can find similar representation for the price of the option. And the main tool for this is Ito's lemma. So once I have the two representations, I equate them because I want the two processes to be exactly equal. And I equate them by equating the drift terms and by equating the diffusion terms. By doing this, we first derive so-called Black-Scholes partial differential equation that the function C must satisfy. So the problem of pricing we reduced to the problem of finding the pricing function C. And now we know that it must satisfy certain partial differential equation. And the boundary condition corresponds to the payoff function. We know the payoff function. In addition, by comparing the diffusion terms, we also find that in this replicating portfolio, the number of shares at any time must be equal to delta. So if I differentiate the price with respect to the price of the option with respect to price of the underlying, I get the delta. So this is formal justification why delta is the right hedge ratio I should use at any time to create a replicating portfolio. It can also, this derivation can be used to justify so-called risk-neutral representation of the price. Price of the option at any time can be represented as the discounted payoff. However, for this, you have to use different measure Q, so-called risk-neutral pricing measure. Again, I am mentioning this because we will be using both P measure and Q measure, and we'll be using this representation. Now, how about finding delta for path-dependent options? Actually, the steps are almost the same. The main difference is I have to add additional state variable. So the critical assumption in this derivation was that the price depends on the current value of the underlying. So this is Markovian setup. If I have path-dependent component, the value, the price of this component depends on the history. So this means I have to add this additional component as a state variable. I increase the dimension of the problem by 1, but I'm back into Markovian setup. So for Asian option, the state variable is simply integral. Clearly, and I will mention this at the end of the talk, there are other ways of defining arithmetic sum. Instead of taking integral, I can take sum, where I sample the process at some pre-specified time points, but it is convenient actually to work with the integral. So after I add this additional state variable, the derivation is almost identical to the previous one. And at the end, it turns out that the proper delta is again equal to the derivative of the price of the option with respect to the value of the underlying security. In addition, we don't have to trade the state variable. Intuitively, this looks like correct approach because over a very short time period, the state variable is perfectly correlated with the underlying security. So there is no need actually to use the state variable as additional hedging tool. So these facts can be formally justified using so-called Mariavin calculus. But for the purpose of this talk, what is important is to mention that the derivative is calculated in exactly the same way. Now, in practice, clearly, we don't rebalance portfolio continuously in time. We do this only on discrete time periods. And because of this, there will be hedging error. This will be difference between our target, which is the price of the option at the end of the hedging period, and the replicating portfolio. So to really see the performance, compare performance of delta hedging with anything else, we need to find a benchmark. And as a benchmark, I'm going to use so-called mean square optimal hedging strategy, where the hedge ratio is determined as a solution to certain optimization problem. So the explanation of the mean square optimal hedging here is in a generic framework. Suppose that, what is discrete framework, discrete time framework? Suppose that I want to hedge value of the option at the end of the period of length h, and at time 0, I set the replicating portfolio. And to simplify the explanation, suppose that interest rate is 0. So at the end of the hedging period, the value of the portfolio, hedging portfolio, certainly typically is not equal to the value of the target. So this means I have to inject or possibly withdraw a certain amount to adjust the portfolio to make it equal to the target. So what are the costs of doing this? The initial cost of setting the portfolio plus the cost at maturity to rebalance the portfolio to make it equal to the target. And at the bottom, we see there is a representation. Sorry, okay. There is a representation of the hedging error. This is the difference between the target and the value of the replicating portfolio. We want to minimize the difference. One metric that we can use for this is the mean square error. So we want to minimize mean square error with respect to the two parameters, initial value of the hedging portfolio and the hedge ratio. We can recognize this as a standard classical regression type situation. We can find easily the two parameters. This is the solution to the optimization problem. We can also notice that on average, the additional cost, the rebalancing, is zero. So it is in a sense a fair situation to both writer and the seller. However, this equation holds only under the P measure because we minimize the hedging error under the P measure. There's no guarantee that similar result will hold under the Q measure. So in this setup, the hedging target is price of the option, but actually it can be any random variable, can depend also on other factors, can depend on the past component, so it is quite general. This framework can be extended to multi-period situation where we repeat this optimization at any time period, and it has been used by some authors to identify proper hedging method, even pricing, in the context of so-called incomplete market models. In our setup, however, we treat the prices as given because we will be using Black-Scholes framework, and we'll be using this optimization component only to identify optimal hedge. So now, how the two methods, classical hedging and mean square hedging, compare in the context of European option? So we have two portfolios or two hedging errors. The one corresponds to the classical standard delta. The other corresponds to mean square. Some authors refer to this as variance optimal. And here is the result. The variances of the two hedging errors asymptotically, when we shrink the length of the hedging period, they actually are the same. So in this sense, delta hedging over a very short time period will behave in almost the same way, will lead to almost the same hedging error as mean square optimal hedging. So this justifies the fact that delta hedging is used by traders. It is still acceptable approach, even if it was derived in the context of continuous time framework. So this result is well known in the context of vanilla options, but it is valid for any European type option. What I only want to mention is that the ratio of the mean optimal hedge or mean square optimal hedge and standard delta hedge has the same main term, is equal to 1. The correction depends on the length of time interval, and it shrinks as h goes to 0. Now, very quickly, why actually delta hedge is working? Delta hedge is determined at the current time. It's unlike mean square hedging, it's not looking into the future. So this can be justified by using very simple payoff where we have a linear function and quadratic function. Since options satisfy partial differential equation, they are smooth function. So they can be approximated locally by quadratic function. And then look at how each method hedges each component. In fact, both mean square hedging and delta hedging, they hedge each component independently because mean square hedging is a projection and projection is a linear operation. So we hedge each component independently. Delta hedging is based on finding derivative, but derivative is additive operator again. So both hedging methods hedge each component independently, and variance or mean square hedging hedges the linear component perfectly. It hedges quadratic component by projecting on the space of linear function. How about delta hedging? So the linear component is hedged perfectly by delta hedge. Why? Because in delta hedge, we calculate the current expected discounted value of the linear function. And it is exactly, again, the same linear function. So which means the future linear component is exactly the same at the current time. And this explains why calculating derivative at the current time is also working in the future. However, the current, the delta hedge hedges quadratic term differently because it uses tangent line to the value of the quadratic term at the current time. So now let's compare the different hedging methods in the context of path-dependent options. And for this, I'm going to use mostly Asian option. For this, we are going to use auxiliary or additional hedging tool, which would be best option to hedge path-dependent option. So suppose that this is what I want to hedge. This is value of the option at the future time. And it depends on the terminal value of the underlying plus path component. I want to hedge this using only underlying security, but at this point, I am not looking only at linear function. I'm looking at general function of the underlying security. So I can minimize the mean square error over all functions that belong to particular set of functions. If as set of functions, I choose linear function, that I am back in the context of linear regression and I know the solution. But if as set of possible hedging options, I consider all square integrable functions, then the optimal hedge will be option with payoff function of this form. What is this? This is actually conditional expectation of the price of the option, knowing terminal value of the underlying security. So this is a well-known fact. If I want to minimize second moment with respect to certain variable, the optimal solution is the mean of this variable. If I do this conditionally on each terminal value, I actually determine optimal hedging option, which will not be a linear one. And this optimal hedging option can be determined for some particular state variables, path-dependent state variables, in particular for integral of the price process. Now, this optimal hedging option has some additional important properties in the context of Black-Scholes model. It depends on the condition process. So if diffusion process is conditioned on terminal value, we call this condition diffusion process. In the context of Black-Scholes framework, the conditional geometric Brownian motion is equivalent to a function of conditional Brownian motion. And this is this representation. So instead of conditioning geometric Brownian motion, rather I can work with so-called Brownian bridge. And this is Brownian motion for which terminal value is known. This process has the property that it is a sum of linear function spanned between initial value of Brownian process and terminal value of Brownian process plus standard Brownian bridge. Standard Brownian bridge is Brownian process conditioned on the value of the process being equal to 0 at maturity. Why is this important? It is important because now the condition geometric Brownian motion no longer depends on the drift process. So if the drift parameter corresponds to empirical measure P, it disappears. It's no longer here, which means the optimal hedging option, its price is exactly the same as the price of option we want to hedge. We don't we no longer have to worry about using P or Q measure. The hedging option is determined under completely different measure, does not depend on the parameters of expected rate of return under the P measure or the interest rate under the Q measure. And now, how do we use this option? Maybe I will skip this, maybe just example. The hedging option in the context of particular path-dependent contracts, in this case, this is geometric average, can be evaluated explicitly. I just want to show the shape of this optimal hedging option. It is nonlinear function. On average, conditionally that I know terminal value, it gives me the right position. And the thin line here, lines here, these are the quantiles corresponding to the uncertain path component when I know the terminal value. And now let's compare the two hedging methods, so delta hedging and mean square hedging for Asian option. So we are looking for Asian option when the strike price is 0, because then we can actually do certain calculations explicitly. In particular, we can find the price of the option explicitly. Here are the simple calculations, simply using Fubini theorem, we can change the order. This is the price of the option that pays amount equal to the integral divided by capital T. So in this case, this is the option we are interested in. The price of the option at any earlier time is a linear combination of the current integral plus certain linear function of the spot price. So this is easy to work with. This will give us the form of the hedging target at the end of the hedging period. It is a linear function of the integral plus spot price. In addition, at time 0, the value of the option is equal simply to a linear function of the spot price, which means I can easily find the delta. D2 actually will be the delta because the integral when h is equal to 0 is 0. So for option that pays arithmetic average based on integral, I can find a representation for the option at any time, and I can also find explicitly the delta. And this means I have a representation for the hedging error. And here is the comparison, how delta hedging compares with the mean square or variance optimal hedging option. So in this case, for hedging, I am using optimal option that depends only on the value of the underlying. So the formulas look almost the same, except that the variance for delta hedging has this factor 4. It is actually 4 times larger than the error for the mean square hedging strategy, and this does not depend on h. So even if I take h to the limit, I will always have this inefficiency of delta hedging for the, in this case, arithmetic average. And this is a result of simulation. I use empirical process by choosing different rates of returns. Actually, should be nu, not mu. And then on the x-axis, we have the length of the hedging period. So once we approach the length of hedging period is shorter and shorter, you can see the ratio of the variances indeed converges to 4, regardless of the parameter of the true rate of return. So we may say the comparison is not fair because now for hedging, optimal hedging, I am using option with possibly nonlinear payoff function. However, I can also find the linear or mean square optimal portfolio consisting only of the underlying and the cash position. So this would be linear portfolio. I can find explicitly the position, and it can be shown that this linear portfolio behaves in terms of hedging in the same way as the optimal option. So the nonlinear component actually doesn't play any role. But now we can look at the hedge ratio for the delta hedging and the mean square optimal hedging. And then we will see that the main terms actually are different. For the delta hedging, we always use twice as many shares as for the mean square optimal hedging. So this is a striking difference between the situation for path-dependent option and European option. For European options, the main terms were the same. The correction was in the second term. For path-dependent options, the first terms actually are different. So delta hedging always assigns twice as many shares as mean square hedging. So because of this, here is a simple graph. If this is the mean square hedging, on average, it gives us the right amount to hedge the risk. Delta hedging gives more than necessary if the terminal value of the underlying security is above the spot price. So if the spot price is 1 and at the end the terminal value is larger than 1, delta hedging is over hedging. If the underlying is below 1, delta hedging is under hedging. So by doing this, actually, it artificially increases the variance. So now, how can we explain the difference in the ratio? So there are several explanations, and here is one probably quite intuitive. Consider an option that pays at maturity return. So this is the ratio of the terminal value of the underlying divided by the spot price. In a sense, it is very basic a path-dependent option because it depends on the terminal value, but also it depends on the spot price. Now, if I calculated the present value of the nominator would be S0, and then it will cancel with the denominator. So if I wasn't careful enough, the price of this contract would be 1 and the delta would be 0. So this would mean I don't have to hedge it. However, if I recognize the situation as the one when I have 1 over S0 number of shares of the underlying, there is perfect hedge. All I have to do is to buy 1 over S0 units of the underlying, and this will give me perfect hedge. So certainly the problem is with confounding between the spot price as part of the payoff and the payoff itself. So a similar problem occurs for so-called guarantees. They are widely used in the context of insurance products. We guarantee the payoff that is at least equal to the initial investment. And this can be recognized as a portfolio of certain investment in the riskless asset plus a call option. So again, if I calculated the price of this and then I wasn't careful enough, I would be, when differentiating, I would also be differentiating with respect to the parameter of the payoff function, and now I would receive incorrect delta. So in the context of path-dependent option, this happens constantly, this kind of confounding between payoff and the known current spot price. And the problem is, how do we disconnect them? So delta hedging, one way of doing this would be say, don't use delta hedging, use always mean square hedging. The problem with mean square hedging is we have to identify the measure, the empirical measure P, which is really difficult, especially to find the expected rate of return. So there are some advantages to using delta hedging. So if we postulate that we would like to have delta hedge, new delta hedge, so that it is determined only under the Q measure, it properly represents the option price sensitivity with respect to the market risk, and asymptotically it performs as well as a mean square optimal hedging, then actually it is possible to do this, and here is the solution. So for this, we actually use, suppose that I want to hedge price of the option at the future time T sub H, and I'm standing at the current time T sub C. So what we do, we calculate the optimal hedging option by using conditional expectation. This hedging option depends on the spot price because the measure I'm using to find the conditional expectation depends on the spot price. But I forget about this. I treat this as a payoff that depends only on the terminal value, like call option. And then I simply calculate delta of this new option. So I forget its dependency on the current spot price. I calculate its price, and then I differentiate this price with respect to the current spot price. By doing this, I disconnect the dependency of the payoff on the current price and the sensitivity today. So how do we apply this? So this will be just one last component. I am close to the end of my talk. All we have to do, again, I mentioned this at the beginning, delta hedging by the very construction should work over a short time period. So I can expand the hedging target using Taylor series expansion. And I use the additional state variable, which is path dependent. And then I find the optimal hedging option for this using conditional distribution for each component. So for components that depends only on the underlying, this is easy. The main challenge is when calculating the conditional expectation for the path dependent component. But we already did this for the arithmetic average. So we know delta for this one. So if I substitute the new delta for the average, I have formula for the corrected delta. And there is additional interpretation here. Formally, I want to hedge a function that depends both on the underlying security and the path component. If I want it, they are dependent. So I am looking at the classical delta looks only at sensitivity along one axis. This one provides more complete differential. So this is something I don't have time to go deeper, but this is another explanation. And maybe finally just example, suppose that now we are looking at fixed strike Asian option over 1 year. I want to hedge value of this option at time. So this is month 11. And I am looking at different length of the hedging periods. Now, as a spot price at the beginning of the hedging period, I choose different points because depending on the curvature of the hedging target, the correction of the delta will be helpful or not. The important component in the hedging is also the quadratic component. So depending how I choose the initial price, the advantage of the new delta is clearly visible. So over x-axis, we are looking at different length of hedging periods. If the main component, the quadratic component, is not large compared to the linear component, the correction is quickly working well. So here we are looking at the ratio of standard deviation, this type, not variances. However, if the spot price, the current spot price of the underlying is close to the option being at the money, the quadratic component is large and it dominates the error coming from the path component. And in this case, the corrected delta behaves in a similar way as the standard delta. Very quickly, other options. Let's look at options that depend on maximum. We can repeat everything what we have done for Asian option. And the main challenge is to find conditional expectation of the new state variable. In this case, it is maximum. Actually, in the context of Black-Scholes model, it also can be found, which means we can compare the standard delta with the mean square optimal delta and the corrected delta. And similarly to the Asian option, we can see that the main term for the standard delta is not the same as the main term for the mean square optimal, and the corrected is twice as large. So this confounding effect appears is valid for any contract. And here is the graph. So for options that depend on maximum, the problem is more challenging because there is high curvature, but regardless of this, standard delta is not the right approach. Okay, I didn't show the ratio of the variances. In this case, it's not possible to calculate explicitly, but using Monte Carlo simulations, the ratio of variances of the standard delta with respect to the mean squared delta converges to 3. So the standard deviation would be around 1.7 larger for the standard delta. Okay, so there's no time for static hedging. Let me just conclude. So what is takeaway? The standard delta for path-dependent options does not represent what many authors claim to represent, namely the dependency of the value of the option on the market risk, because it includes also the current spot price, which no longer has the same impact on the future value, or is irrelevant in the context of path-dependent options. As a result, when using standard delta, we artificially increase the size of the hedging error. So it is possible to provide correction to the delta, and for this we don't need to know the empirical measure P. The overall gains will depend on the size of the path component with respect to the quadratic component. And as I mentioned at the very beginning, I illustrate these results in the context of Black-Scholes framework, but these are asymptotic. So for general models based on diffusion type dynamics of the underlying securities, all the analysis presented here is also applicable. So maybe I will conclude at this point. Thank you very much for the attention, and I will answer questions if there are any.
Thank you, Professor. That was a very nice and I mean, even not from the area, easy to understand and follow its functions. Thank you for your nice presentations. I allowed our participants to unmute themselves and ask questions. I kindly ask them to raise their hand if there are more than one. And so just let's take some questions if there are any from our participants. It seems that they all are very happy. Okay. I would like to ask if this is related. I'm not very much 100% sure, but for the delta neutral position, what is it considerable to have a kind of house with the speed or rate of return to the delta neutral for the proposed approach?
Yeah, so this is terminology also used by certain authors to make a position delta neutral. We have to somehow quantify the sensitivity of our position with respect to market change. And the usual delta for European option really represents this properly. But this work demonstrates that if in our portfolio we hold position in any path-dependent contract, like American contract, the usual derivative does not make our position neutral, because does not quantifies properly the dependency or the sensitivity of the portfolio with respect to the change in the value of the underlying security. Yeah, so this work, I would say, is still not well publicized. Probably my mistake was to put in the title of the paper Asian. because it emphasizes somehow, or it makes impression that this is applicable only to Asian option. I didn't have time. I got involved in other projects. Only now I look back, or I'm looking now at other situations, and in particular ways of correcting the delta using at the level of portfolio, not individual contract. And typically at the level of portfolio in practice, this is done through numerical methods where we use a finite difference to approximate derivative. So I'd like to be able, and I think I'm on the right track right now, to have a way of somehow addressing this deficiency of standard data in a more general way at the level of portfolio, not level of individual contracts. This probably will make this fact better known among practitioners, and be aware that the usual delta in the context of path-dependent contracts is kind of meaningless, at least in my opinion.
I mean, no, that's a good point. What it came to me as well, that these strike values, they are most of the time are chosen according to the position of the market. And yeah, of course, this is also very much determinant on how the deltas or the other indicators are going to behave. And it is all not one-to-one, cannot be corresponded, but as you are from the actuarial branch as well, that these strike price is very much reminding or can be put into a form of the reinsurance stop-loss contracts. Yes. But not having any, I mean, the asset approach on the background, but this variability is also a very important component on that too.
Yeah.
Yeah. Okay, I'm just checking once again if anyone is writing any questions. So, I mean, I'm very much pleased to have you. We are all, and I would like to give, at least with our participants, our reactions as an applause to you. Thank you very much for having time and preparing such a nice presentation for us.
Thank you very much for the invitation. It was my pleasure to be for 1 hour in the beautiful country. This would be would be the third time, but all my previous visits were relatively short. It was part of being on a cruise, but I always enjoyed very much being in your country.
You're welcome always. We will be very happy to have you. So thanks to participants. We have really a very good participation. And take care of yourself. I hope to see you again.
The same to you. Yeah. So I'm going to send you the slides.
Okay. Please. Thank you.
Thank you. Bye-bye.
Bye.